Okay, this is the second half of the video that covers Unit 6, Notes Part 1 on reaction rates and reversible reactions. So we're going to dive in. We're about maybe more than 2/3 of the way through the notes here, but we're going to look at reversible reactions first. And you notice with this equation, there's something a little bit different here than we're used to. We have a double arrow, and the double arrow means this is a reversible reaction. When you have the double arrow, what we mean is the reactants, in this case N2 and H2, are becoming ammonia at the same time that ammonia is going back and forming this stuff. And Fritz Haber, who came up with the ammonia production we talked about earlier this year, he was trying to make ammonia to make explosives for Germany in World War One. It also had the consequence of helping make fertilizers, which are ammonia based. He would put nitrogen and hydrogen and react them in a tank and get ammonia. But what he found was the ammonia would immediately decompose back into those guys, and those guys would again react and go back and make ammonia. And there'd be this cycle of those guys going just back and forth in there. And so he had a hard time getting enough ammonia out of that to make it worth the time and the effort and the money. So we'll look at how he fixed that later in another set of notes. But reversible reactions just go in both directions. Products are being made just as quickly as reactants are being made, and vice versa. Now, we do label the left side as reactants all the time. Even though it's being produced in a reversible reaction, we've got to come up with a labeling system so we don't get confused. So it's reactants on the left, products on the right, just like it always is in that. Okay, let's go to the next slide. And let's look at chemical equilibrium and what that is. Okay. When the rates of the forward and reverse reactions are equal, we are at equilibrium. What I usually do is use an example of classrooms. And so let's say we're in our room at school, and across the hallway is another room. And in our room, we have, let's say, 38 students. And let's say the other room has 21 students. Well, let's say that I decide to start sending 2 students to that room, and that teacher says, you know what, I'm going to send 2 students to your room, and we do this every minute, 2 students per minute getting sent back and forth. Well, what's going to happen to these numbers in those rooms if we send 2 there and they send 2 to us? Well, what's going to happen is nothing. If we're sending equal amounts back and forth, the 38 and the 21 are going to stay constant. That is an equilibrium situation with people going back and forth between rooms. If the amounts in a container of reactants and products don't change, but they're going back and forth in equilibrium, you're going to see a state that is known as chemical equilibrium or dynamic equilibrium. And at the macro scale, it often looks like there's nothing happening in the container unless there's a color change or something with the reaction. But at the microscopic, not even the microscopic, at the subatomic and the atomic levels, you're going to see a lot of activity, which is where we get the word dynamic chemical equilibrium from. So no net change occurs in the actual amounts of reactants and products at equilibrium. Another example of chemical equilibrium, besides the classroom one, is escalators at a mall. Let's say we're at Fashion Fair at Macy's or something that's got escalators. If you have one person going up an escalator and 3 people going down on the down escalator, that is not going to be in equilibrium. However, if we can get 3 to go up and 3 to go down, then we're looking at a situation that would be, equilibrium. The amount of people on the top and bottom floors will not change if 3 go up and 3 go down at the same time. So we look at equilibrium and we say it's about the rates of the reactions. The speed of the forward is the same as the speed of the reverse reaction. However, the concentrations might not be the same. And if they are the same, that's a coincidence. It has nothing to do with equilibrium. So if we look at this example down here, we have a hypothetical reactant A and hypothetical product B. And A is forming B just as quickly as B is forming A. But you notice the longer arrow shown in this. We're showing that A is becoming B and B is becoming A at the same speed, but at equilibrium, we have a lot of B in the container. And so if you notice, the container's 99% B and 1% A. And we say that the equilibrium position then is shifted to the right, meaning they're both going at the same speed, but at equilibrium, there's a lot of B in the container and very little A. Now we could go back to the classroom example, and let's say that we started with 38 kids in one room, but let's say the other teacher just had 2 kids in that room, and we kept sending back and forth 2 kids. Well, the numbers are still not going to change. We're still at equilibrium, but 38 is way bigger than 2, still in equilibrium. Okay, so equilibrium position is about how much product or reactant you have when it's at equilibrium. Catalysts are often brought up in this discussion. And so you notice catalysts are pretty easy in equilibrium. They speed up everything. So they speed up the forward and the reverse reactions, and because they're opposites of each other. So if I put a catalyst in there, it's going to do both. Okay. What it does change is the time it takes to get to equilibrium. So let's say we start reacting some stuff, and initially one reaction is going to go faster. So like if we're going from our A to B example, I put A in the container, and let's say that it starts turning into B. Well, as B starts to form, then it starts turning to A. And if I throw a catalyst in there, it's going to get to equilibrium faster. Okay. In that case. And Haber used a catalyst in his reaction. He was trying to get more ammonia out of the thing, but he ended up speeding up both reactions with it. We're going to see later how it actually helped him to do that anyway, even though it sped up the ammonia's conversion back to N2 and H2. And we'll see how he used a combination of things to get it to make more ammonia when it naturally wants to just kind of stay as N2 and H2. So that's a little bit on reversible reactions, equilibrium definitions, and things like that. Okay, we'll hit this topic some more later this week.